So now our objective is to understand what do you mean by Cauchy product. So as we have given two numbers a and b, we know how to multiply these two numbers. The same concept is applicable for if you given a two sequences an and summation of bn. How to multiply these two sequences, and then later on the questions is arise if you multiply these two sequences whether the new sequences produced will be convergent. If an is convergent, bn is convergent, and suppose that the new, when you multiply these two series, a new series is appear, that is, let's say summation of cn, will it be convergent? That is the question. So in this we'll discuss that under which situation this summation of cn is convergent and how to do the product of these two series, and which is known as a Cauchy product. So to define a Cauchy product, we'll need an, summation of an and summation of bn are the two series. Then the Cauchy product, that C0, and I can say this is Cn, is defined as C0 is equal to A0 into B0. C1 is A0 B1 A1 B0. C2 is A0 B2 A1 B1 plus A2 B0. It's simple product. If you have, see, if you have two number A0 B0, then you multiply in this two manner. If you have two number A0 plus A1 and B0 plus B1, then the product of this two can be done is A0 B0. But in that, this is not the way we can do it. In this manner we have to do A0 B1 A1 B0. That is the middle term of that. A0 B1 A1 B0. First term and last term we have to remove from this. So this way we will not do that. And same way, if you can do it for further for any n term, that is A0 Bn plus A1 Bn minus 1, A2 Bn minus 2 up to so on, An B0. Then the series summation of Cn, it's called Cauchy product of summation of An and summation of Bn. So this is known as a Cauchy product of An and Bn, summation of Cn. As I have told that the question arises is if summation of An is convergent and summation of Bn is also convergent, whether the summation of Cn is also convergent. If not, under which situation it will be there. So first, the answer for that question is no. If summation of An is convergent and summation of Bn is convergent, we cannot say that summation of Cn is convergent. We'll give the counter example for that first. So let us consider this summation of An equal to summation of Bn equal to summation of minus 1 raised to n minus 1 upon root n. And why this is the alternating series. And this alternating series is convergent, which we can easily prove by Leibniz test. If you can recall what is Leibniz test, which says that the alternating series summation of An minus 1 raised to An into minus 1 raised to n into An is convergent. It should satisfy the three conditions. The first one is An is greater than or equal to 0. The second one is sequence An is decreasing. And the third one is a limit of An is 0 as n tends to infinity. So this is known as a Leibniz test. And using this Leibniz test, this summation of minus 1 is to n minus 1 upon root n is convergent. Because what is An here? As per this, not this An. Here An is minus 1 is to n minus 1 upon, but according to this notation, The an is 1 upon root n, which is positive. 1 upon root n is a decreasing sequence, and limit of 1 upon root n is as n tends to infinity will be 0. So we note that the summation of minus 1 raised to n minus 1 upon root n is a convergent. So that means summation of an is convergent and summation of bn is convergent. Now let us look at the Cauchy product of these two. That means what is the Cn? So Cn, as we have defined earlier, that is, we have summation is now start with 1 to infinity, because in the denominator if it is undefined, so that's why it is summation start with 1 to infinity. So that's why instead of starting with 0 to this, we'll start it with 1. So it is 1 bn plus a2 bn minus 1 plus a3 bn minus 2 up to so on an b1. So as per this, a1, that we know it is a positive n equal to 1 upon 1. So it is 1 into bn minus 1 is minus 1 raised to n minus 1 upon root n. a2 is negative sign, so it is minus 1 upon root 2 into n minus 1 minus 1 raised to n minus 2 upon root n minus 1. Then it is minus 1 square into minus 1 raised to n minus 3 upon root 3 into root n minus 2, and so on. The last term is b1. b1 is 1 as per this, minus 1 raised to n minus 1 upon root n into 1. And if you combine all of them, then you can observe that in the numerator minus 1 raised to n minus 1 is common out, and the rest of the things what we can have, it is 1 upon root n plus 1 upon root 2 into root n minus 1 plus 1 upon root 3 into root n minus 2 up to so on 1 upon root n. If I take the modulus both sides, then this minus 1 raised to n minus 1 will go on away. I can say this is greater than 1 upon root n plus this quantity 1 upon root n into root n. Okay, so we have just using the concept that 1 is greater than 1 upon root n. In the same way, 1 upon root 2 is greater than 1 upon root n. That is 1 upon root 2 is here. That I can say it is greater than 1 upon root n. So plus 1 upon root n into 1 upon root n. The same way we can say that 1 upon root 3 is greater than root n. And so in the last one also we have using that. But what is this quantity? Will be have 1 upon n plus 1 upon n up to 1 upon n times. So it is n upon n, which is 1. So I can say that summation of Cn is greater than 1 for any n. And to having the summation of summation of Cn is convergent, the limit of Cn has to be 0. So by 0 test, or I can say limit test, we can say that the summation of Cn is divergent, because limit of Cn is not equal to 0. So I can say therefore a limit of Cn is not equal to 0 as n tends to infinity. So therefore the summation of Cn is divergent by limit test, or I can say 0 test, whatever you want to use, any one of them. So ultimately what we have achieved by this example is that summation of an is convergent, summation of bn is convergent, then it does not imply that the Cauchy product of these two will be summation of cn, or it rather than it is not convergent, we cannot say. So the next theorem tells you regarding the same thing, that under which situation, that means if summation of cn is convergent, summation of an is convergent, summation of bn is convergent, and summation of cn is convergent, if all the three are convergent, then you can write down this product will be equal to a Cauchy product of cn. So let us write the statement of this. If the series summation of n running from 0 to infinity an, summation n running from 0 to infinity bn, and summation n running from 0 to infinity cn are convergent, where cn is a Cauchy product of an and bn, then prove that summation of an into summation of bn equal to summation of cn, n running from 0 to infinity. So this is the theorem. It tells that if all of them are convergent, then we can say that the product will be this. So we'll actually prove this statement using the Abel's limit theorem. So for that, so I can say this theorem is an application of the Abel's limit theorem. So for that, let us consider fx is equal to summation of an x raised to n, as n running from 0 to infinity, for all x which is less than 1. Since summation of an is convergent, which is given, limit of an as n tends to infinity is 0. So for epsilon equal to 1, there exists n0 belongs to n such that mod of an is less than 1 for every n greater than or equal to n0. So therefore, I can say that mod of an x raised to n is less than mod of x power n for every n greater than or equal to n0 by multiplying mod x power n is there. So therefore, what we can say, a summation of an x raised to n is less than or equal to summation of mod of an x raised to n, which is, according to this, it is summation of mod of x raised to n, which is which is convergent, as your x is between -1 and 1 due to the geometric series, or mod x is less than 1. Due to this geometric series, we can say that it is convergent. So we can say that summation of an x raised to n is convergent. Since this is convergent and summation of an is convergent, if you recall the Abel's limit theorem, which says that if this is summation of an x raised to n is fx and summation of an is convergent, then we can say that, so by Abel's limit theorem, we say that limit of x tends to 1 minus fx is equal to summation of an. And similarly, what we did for summation of an x raised to n, the same calculation or same situation, we can do it for bn x raised to n and for cn x raised to n. So for En and Bn we have did it. So for that similarly, we will do for similar statements are true for the power series Gx is equal to summation Bn x raised to n running from 0 to infinity, and Hx equal to summation n running from 0 to infinity Cn x raised to n. And a limit of Hx as x tends to 1 minus by Abel's limit theorem, it is h of 1. H of 1 is summation of Cn, and limit of g of x as x tends to 1 minus is g of 1, which is summation of Bn. Now we'll start with this side, summation of Cn. Ultimately, our objective is to prove that summation of An into summation of Bn is equal to summation of Cn. That is our objective. So for that, I am starting with summation of Cn. Summation of Cn, as per this, it is h1. That is equal to a limit x tends to 1 minus h of x. But as per the Cauchy product, a limit x tends to 1 minus, this is fx into g of x. But the limit of product is product of limit. Due to that, we can write down this is limit x tends to 1 minus fx into limit x tends to 1 minus gx. So hence this is equal to f of 1 into g of 1. F of 1 we know it is summation of An, and g of 1 we know it is summation of Bn, and which completes the proof of the statement that summation of Cn is equal to summation of An into summation of Bn. So this Cauchy product is actually an application of Abel's limit theorem, and which can be also did in another manner, which probably you have discussed in your analysis